We're live. All right, so we're going to go over your 2 quizzes. So that's the first thing we're going to do to review today. Then I'm going to kind of scroll through. You're not going to see it, but I'm going to scroll through the multiple choice and free response and just point out a couple of things that I think you should focus on. So you'll have a good idea of where to begin. And then I'll be more than happy to, as I'm scrolling through and things that you need to focus on, if you're not quite so sure of it, then I'll be happy to answer some questions, maybe do an example or something like that. Another thing that you can review that we're not going over today that we went over last week was those free response problems. Do y'all remember what I'm talking about? Okay. You need those? Okay. Just remind me at the end of class that you need those. Okay. And so those free response questions will be really good for your free response section as well. I personally think y'all should do really well on this test. I'm going to try not to get,
Please aim for
high
a
hopes.
C, and please, we get an A or a B, then,
There you go. High hopes, low expectations.
This is
That's what I'm going to go in this with, and then we'll see. Hopefully we fall somewhere in there. Okay, so high hopes, low expectations. But I really think that y'all will be pleasantly surprised on the test as well. I think you can handle it.
After this test, is there how many more?
There's one more test that you'll take as far as an official unit test after this one. So we'll do one more unit, and then there's a couple of things that we're going to review, but we're not going to take an official test of. Does that make sense? Because there's a couple of things we did last year in pre-AP that I need you to remember, like your gas laws, like P1V1 equals P2V2. Easy stuff like that, we'll maybe spend a day doing gas laws and then a day doing a few things from solutions from last year that you might not remember, and then we're just going to review for the rest.
So, like IMS or anything like that?
That's next. IMFs is next, and that's going to be your last official unit test, is your IMFs. Yes, sir.
Yeah, we aren't allowed a group from this test.
No. This is going to be an individual test.
Are you able to be bargained with or reasoned with in any type of way?
even
No.
if you probably
Even if I get you a pound of food?
I think
Okay.
last year figured it out.
All right.
I mean, I got $1.
Yeah. All right, y'all ready? We're going to start with the quiz that you did on your own notebook paper. So that's the quiz I'm going to start with by going over it. You can take those quizzes home tonight to study with if you want to. I just have to have them back tomorrow. County policy, I got to keep everything graded. Huh? I don't care. If you want to draw a line and write on the bottom on stuff that you're going to study with tonight, that's fine. I would just make sure you don't do it right beside where you did it, because I may have messed up grading. So if you're writing up top, then I'm going to think you did it. But if you'll just circle it.
I graded D, so if that grading is messed up, then
There you go. So
Yeah, that's
you can
probably-
just,
that's 10 out of 10.
you can let me know. All right, A says draw the Lewis electron dot structures for PF3 and PF5 and predict the molecular geometry for each. So let's start with PF3. So phosphorus has 5 valence electrons, fluorine has 7, and there's 3 of them. So 5 plus 21 is 26, divided by 2 is 13. So I know I need 13 pairs of electrons. So I know phosphorus is going to be in the middle. Then I have fluorine, fluorine, fluorine. Put my lone pairs around fluorine. And it's a good thing that this is only 12, and I need an extra one because, of course, phosphorus would have to have 8. Okay, so this gives me 13 pairs of electrons. And if I asked you for the molecular geometry, you should tell me that this is trigonal pyramidal. Okay? Yes, ma'am.
and you know it's not trigonal planar because
Because of the lone pair. Yes. Okay. So it was +1 for the drawing, +1 for the trigonal pyramidal.
we have to draw it that way for 2025.
You don't, and somebody else asked me because they drew it like this. That's fine. Okay. The only reason why I like to show the fluorines are pointed down is because I know this lone pair has caused them to be pushed down. Now, do you have to? No. Do I think they would count it off on the AP exam? No. But I just think if it's something that you know is going to happen, why not? Sometimes it'll keep you from messing up, like when they ask you something about bond angles. Because I can clearly look at this and know that my bond angles are steadily decreasing. Does that make sense? Okay. All right. B. Oh, sorry. Wait, I didn't draw PF5, did I? So 5 valence electrons for phosphorus, 7 for fluorine. There's 5 of them. 5 plus 35 is 40. 40 divided by 2 is 20. So I know I should have 20 pairs of electrons. And if I draw 5 fluorines bonded to the phosphorus, and I put my fluorines around it, I put my lone pairs around my fluorines, that gives me 20 pairs of electrons. And so the electron geometry for this is trigonal bipyramidal. So +1 for the drawing, +1 for the answer. Double check yourself, make sure I didn't grade you wrong, because you know it's bound to happen at times. All right, any questions about those two things? Everybody good? Everybody know how I drew them? Feel good about that. Excellent. B says, is the PF3 molecule polar or is it nonpolar? Explain. So you should have looked at PF3 and you should have said this is polar. And you got 1 point for saying it was polar. And I know I graded some of these wrong, so again, double check me. Okay? So you got 1 point for saying it was polar, and then you got 1 point for your reasoning. And your reasoning didn't need to just be because there's a lone pair of electrons. Okay? Now some people may have gotten to slide with it. I'm not sure. All right, but this lone pair of electrons is what is making this molecule polar. But what is that lone pair of electrons doing that makes this molecule polar? Okay? There you go. It's pushing these fluorines what? Down. It's pushing the fluorines down, which is causing the charge to be distributed how? Unequally. That's what makes it polar. Okay? So, the lone pair of electrons, right, is pushing the fluorines down, which is causing the charge to be distributed unevenly. What happens if the charge is distributed evenly? It's nonpolar, even if, is fluorine more electronegative than phosphorus? Yes. So is fluorine hogging more of the electrons than phosphorus? Yes. But if it's happening equally all the way around the molecule, what happens to those polar moments? We say they what? We say they cancel. Okay? So that's why you need to make sure that you include in your explanation that the charge is being distributed unevenly. That's what makes it polar, is because it's being distributed unevenly.
Do we have a study session later?
I will. I'll be here early tomorrow morning.
Because I need that.
C. On the basis of bonding principles, predict whether each of the following compounds exist. In each case, explain your prediction. So you should have said that NF5 cannot exist. That was +1. And you should have said that arsenic pentafluoride can exist. That was +1. So you got 1 point for each of them, just knowing if they existed or if they didn't exist. All right. Then the second point on each of those had to come from the fact of why. Why can nitrogen pentafluoride not exist?
Has no d orbital.
Thank you. Awesome, Zach. I'm very proud of that. Okay? Because nitrogen has no d orbital for an expanded valence. What do we normally say? How many valence electrons maximum are we looking for here? 8. But if nitrogen has 5 things bonded to it, hang on, sorry. My smartboard's got to catch up. There we go. If nitrogen has 5 things bonded to it, or not, there we go. How many valence electrons does it give nitrogen now? 10, right? 2, 4, 6, 8, 10. Right? Okay. Now, that can happen if I have a d orbital. Why? Because I can expand into that d orbital and put my extra electrons there. Nitrogen's only in the second period, though. How many energy shells do we have in the second energy level? S and a what? P. How many electrons can I fit in an S? 2. How many can I fit in a P? 6. So how many total valence electrons can nitrogen have? 8. And it can't have any more because there's no d orbital in a second energy level. Does this make sense? Yes. When we look at arsenic, arsenic is in period 2, 3, 4. Okay? Now anything in the third energy level or greater can have an expanded valence. Okay? Why? Because once we get to that third energy level, what have I added? I have an S, I have a P, and now I also have a what? D. So I can expand that valence. We call it an expanded valence because now just instead of having 8, I can go all the way up to 12 electrons if I need to, which would be how many bonds? 6. Does this make sense?
Yeah.
So that's what you should have had. Because it has a d orbital that it can expand into. Important thing is, if you didn't get it then, do you get it now? Yes? Good. As long as we can get it before the test, then we are A. Okay, this will be the last test grade for this 9 weeks, by the way.
Wait, I'm not just kidding.
Because your next,
After prom doesn't go.
it goes on the 4th 9 weeks. So, oh, the day after prom. That's going to be a lovely day.
Wait, after
Is this nice?
I'm probably not even in there, so
probably
I'm
not
not going to sleep.
Oh, I have to present the day after prom. I mean, I'm going to be there till midnight cleaning up. I might as well as go sleep in Wetumpka parking lot too. I'll just meet y'all there, okay?
Build a need.
We'll just all go sleep in our prom finery.
But I say, I don't know about anybody. I mean,
I
I'm not gonna get up
cannot
there.
do
Last year we had it
All right.
that last, we had like that last year, and I had all the intentions of going, it just didn't happen. So I'm not even expecting to go this year.
All right, that's cool. All right, A, the compounds SF4 and BF3 react to form an ionic compound. I'm on that second quiz now, by the way. According to the following equation. Number 1 says draw a complete Lewis structure for the SF3 positive cation and SF3 BF4. They're asking you to draw this, SF3 positive. So all of you who tried to draw SF3 BF4, that is not a possibility. And I'm not looking at anyone in particular because I don't know who did it. I don't even know if it was this class period. But I know somebody, actually 2 people in my classes, tried to do it. Okay? This is an ionic compound. Are these 2 things bonded together because they are sharing electrons? No. That would be a covalent bond. These 2 things are bonded together because this is positive and this is negative. Yes? Yes. So I cannot draw these 2 as one molecule because they're not one molecule. Okay? They're a positive that's attracted to a negative, and then they just start stacking up and up and up until I get a lattice structure. Okay? They're not an actual molecule. You cannot take it as a molecule. Okay? All right. So if I drew the SF3 positive, sulfur has 6 valence electrons, fluorine has 7 times 3, and I have to subtract 1 because this positive means that I have lost an electron. Okay? So 6 plus 21 is 27, minus 1 is 26, divided by 2 is 13. So this looks a lot like the last one we had to draw, where sulfur's in the middle. We have fluorine, fluorine, fluorine. When I put my lone pairs, I quickly realized that that's only 12, so that last lone pair has to go on my sulfur. And because it is positive, I put it in brackets, and I show that the whole thing is positive. Now, I did not count off if you did not put brackets and show that it was positive. If you do not put brackets and show that it is positive on the test, I will count off. Okay? Those are things you got to remember. Those are simple things. We can put it in brackets and put a positive symbol, okay? That's real easy. All right. So, that was the first point. The second thing was you had to identify the type of hybridization on the sulfur. So I look and I see 1, 2, 3, 4 areas of electron density. So I know it should be sp3. That was +1. Now, if you drew it a different way, but you put the correct hybridization for the way you drew it, you still got credit. Okay? But I can double check that if you're not sure about it.
So like, where can you
Yes.
kind of briefly run the hybridization?
I will. Okay. Or actually, I'll do it now, Bella. So remember, with hybridization, all you do is count the areas of electron density. Okay? So it asks me for the hybridization of sulfur. So I say, here, I'll do it in a different color so we can see. Here's 1, there's 2, 3, 4 areas of electron density around sulfur. Okay? So that means S is 1, and then P has 3, so if I do 1 plus 3, that gives me how many? 4. Does that make sense? So that's how we get hybridization.
You like the central atom, basically.
Or whichever one they point to.
Okay.
Like on your free response practice, they pointed to a carbon and said, what's the hybridization around this carbon? So you just count the areas of electron density around that
So it's
carbon.
just like 3 areas, it'd be like SP2.
Yes, if it was 3 areas of electron density, it'd be sp2. If it was 5 areas, it'd be sp3d. Does that make sense?
So like, once the P fills up with 3, you go into D.
You go into D.
And then D goes over.
You can only go up to 2 because remember you can only have 6 bonds. So the largest hybridization I can have is sp3d2. So I can have sp, sp2, sp3, sp3d, and sp3d2. Those are the only 5. You may write them down. Well, just in case. You can have sp, sp2, sp3. Let my smartboard catch up. SP. Okay. It's going to shut down soon. I feel it. SP3D. SP3D2. Good. Those are the only ones you can add. All right. 3 says identify the geometry that is consistent with what you drew. If you drew what I drew, you should have gotten trigonal pyramidal. Plus 1.
I know I should put triangle on it, but I should put pyramidal up and down.
Okay, and you know it's trigonal pyramidal because the lone pair pushes them down.
Because the lone pair is pushing them down.
Okay, how could you tell if it's 5 pyramidal? Is that if it has 5
It's
points?
got 5.
Thank you.
You're welcome. Like if I had, like let's say I added 2 there, Bella. If I would have added 2 there, then it would be trigonal bipyramidal.
And trigonal planar, it doesn't have a lone pair.
It doesn't have a lone pair, you're correct. It's just flat. If it's trigonal planar. 4 says predict whether the FSF bond angle in the SF3 positive cation is larger than, equal to, or smaller than 109.5. Justify your answer. You should have said
First you gotta draw the, yeah, draw it.
That's
That's about it, I draw it.
smaller. Well, this is the drawing.
Oh, there's, okay.
Yeah.
Right here.
Okay?
Yeah, I
So you should have said smaller. Why is it smaller? What is this lone pair of electrons doing to these fluorines?
creates a smaller angle.
It's pushing them down, which is causing my angle to do what? Decrease.
That's
Okay.
what you had to say.
I
thought it was something-
Get
that's
half
what
a
I
point
put.
for smaller.
I knew it was smaller, and I knew that was why, but I didn't think, I figured you had to have
That's
like
it.
some fancy like.
Because remember, let's say, and I don't even know this if this is possible, so don't start drawing this saying this is a real molecule, all right? Let's say I drew this, okay, SF4. All right, what shape is this molecule?
Tetrahedral.
Tetrahedral. What's the bond angle for tetrahedral?
No, wait,
109.5 degrees, which is what they asked you in that question. Okay? So everything is evenly spaced out. So if I asked you if this molecule was polar or nonpolar, you would say what? Nonpolar, because all of the charges are being distributed evenly.
How can
However
have
you want to
that?
say it. I'm good with any of them. Okay? Everybody good? Now, what happens when I get rid of that sulfur and I put a lone pair right there?
Comes not equal.
It causes these fluorines to do what?
Push.
Push down. So now my fluorines that were there are now hanging out down here. So what happened to this angle? It decreased. Why? Because those lone pairs were causing those fluorines to be pushed down. What is the bond angle here?
Isn't it 107? No, that's, yeah, okay.
107 degrees.
Can we make mints the same way we make that aspirin or whatever?
Can we make
Just change the
mints?
ingredients?
I mean,
That'd be
yeah,
kinda cool.
probably. You want to make mints?
I was just thinking of these and I was like,
Oh,
I wonder
yeah.
if we could make those because I was thinking how we did that.
Let's make something we can eat, like actually.
Yeah, I'm sure we can make
Banana
mints.
pudding.
Ah.
Wait,
That's a science
no, that's how Miss
experiment.
Barton explained
All right.
the electron cloud theory and all that stuff with pudding
Mystery
and
slime
Oreos.
format.
All right, we ready? Last part of this quiz. Says draw a complete Lewis structure for the SF5 negative anion and CSSF5. So if I draw SF5 negative, sulfur has 6 valence electrons, fluorine has 7. There's 5 of them, and now I have to add 1 because that negative means that I added an electron. So 6 plus 35 would be 41, plus 1 would be 42. Divided by 2 is 21, so I need 21 pairs of electrons. So if I drew this out, put my sulfur in the middle, I've got my fluorines. When I count up, after I do my lone pairs around my fluorines, I realize that that's only 20, so my extra lone pair has to be on that sulfur. And since it is negative, I put it in brackets and I show that overall this whole molecule is negative. Right? Right. All right. 2 says identify the type of hybridization exhibited by the sulfur atom. So I count how many areas of electron density there are. 1, 2, 3, 4, 5, 6. SP3, D2. 1, 2, 3, 4, 5, 6. Yes? Yes. 3 asked you to identify the geometry, and I said you did not have to do that. All right, but I'm going to go over this geometry with you. Okay? First of all, I'm going to tell you the geometry is seesaw. Okay? Now, before you look at me like you are crazy, it is not like any seesaw I've ever seen, don't think about the outdoor seesaws. You remember the seesaws in elementary school that you would get super pumped if they brought out the ones that were white and they went like this, and they had the red little seats that hung down, and you would sit on the seat and you and your partner would just rock back and forth.
They never got them out. So like, I was
Probably because y'all were out
Yeah,
of
but
my
that's
class.
because
Yes.
they had to take the seesaws out of our school because one kid fell off and broke his arm.
On the indoor ones?
No,
It's
I don't
probably
know about
because
the
our
that.
outside
class,
ones.
they came after us, and we were Love Island class.
Yeah. we-
Anyway, the indoor seesaws looked like this, and they were literally, I still remember them, red, white, and yellow. They were just so much fun,
I
okay?
think they got rid of them.
Like, really? Oh, that's so sad. Okay, well, the indoor seesaws are the best, okay? They're a lot more fun than the outdoor seesaws. Nobody likes the outdoor ones. Everybody loves the indoor ones, okay? So, think of this as your seesaw, okay? So, let's talk about SF5. Now, if we had just SF5 with no lone pair, we would split everything out, right? Yes? But what happens when I put that lone pair on that sulfur?
Shoves everything down.
It shoves everything down. So these fluorines are going to come straight out. Do we see that? Pretend like they're not there. And then it makes the shape of a
Seesaw.
seesaw.
So is that the actual?
It's called a seesaw shape, yes.
No, for real.
Yes, we call it a seesaw.
You hate it when they come out there.
Okay.
You can
Huh?
tell-
You're too excited about it.
Because it makes sense. It's exciting when things make sense.
Doesn't even have any seats.
No, it's okay. It's not literally a seesaw. Yes, these two fluorines up top, those are the seats.
You know they got
What
bored.
are they attached to though?
Okay,
They started just getting bored with
Gravity.
geometry. They were like,
they're attached to gravity.
Gravity, so they should be able to go.
I mean, first they came out with, tetrahedral and trigonal bipyramidal and all these awesome, and then they finally were like, okay, we're done.
I got a question
We
for
ran
you
out
after you
of
stop
words.
recording.
Okay. All right. 4 says identify the oxidation number of sulfur in the compound CSSF5. So I have CSSF5. So cesium is in group 1 on the periodic table, right there, number 55. So it has an oxidation state of +1. Because remember, it only has one valence electron. So what does it want to do with that valence electron? Get rid of it. Okay? Fluorine is in column 7 or 17, depending on how you want to look at it. So it has how many valence electrons? 7. So what does it want to do?
Okay, take-
Add 1. So its charge is a -1. Do the ones that you know first. Fluorine's always -1. Always. Cesium's always +1. Now, I have 5 fluorines, so altogether, they're going to give it a charge of what? -5. So I've got a -5 and a +1. This is a neutral molecule, so what does sulfur have to be? +4, right? Do we see that?
so, yeah.
Because these two would give me a +5. +5 plus -5 would give me 0. So the answer was +4. Yes?
Okay.
Do we have questions about this? No? We're good. All right. Let's talk about some things that you need to know for your test.
Jesus.
Jesus is a good one to know. All right.
No, future
Prayer
was wrong.
with Monroe.
All right. I will count it wrong, just so you know.
I mean, that's sweet, but not really.
All right. First of all, you need to know the difference in the 3 types of bonding. So if you'll look on page 15 of that first set of notes I gave you, there is a list where it has covalent, ionic, and metallic on the types of bonding. So you need to look at those, and you need to know that list. It's on page 15 of that first packet of notes that I gave you for this unit. Yes, that page right there. Okay. So I would make sure that I reviewed that page because there are several questions. Okay, because there are several questions that come from that. You're also going to get a lot of questions of things like which one of these does not contain a pi bond or which one of these does contain a pi bond, okay? You can only have a pi bond if you have a what? Double or triple bond, okay? So if it's asking you which one of these does not have a pi bond, then I am looking for everything that has single bonds, right? Excuse me, don't move around too much. It's going to cause a bunch of stuff on here. Okay? All right, make sure you know your geometries. So make sure you know your linear, your trigonal planar, your bent, your trigonal pyramidal, your tetrahedral, your trigonal bipyramidal, and your octahedral. I think there's 7 of them. Does anybody want me to write them down? Linear, trigonal,
Can we go
planar.
all over those?
Huh?
Can we go over those?
Yes, we can.
Because I've never got that.
Trigonal pyramidal,
And you also know when you put a double bond,
tetrahedral, bent, trigonal bipyramidal, and octahedral. All right. Linear is just when I have 2 things bonded together, like something like HCl, or I have maybe 3 things that are bonded together, but they form a straight line like that. Okay? So both of these would be linear, and the bond angle on these would be 180 degrees. Okay? because I can only go from there to there, which is 180 degrees. Okay? Trigonal planar is when I have something with 3 things bonded to it, no lone pairs, which means everything is at 120 degrees, split evenly. Okay? Trigonal pyramidal is when I have 3 things bonded to it, but I've got a lone pair, so it's pushing them down. So I'm at 107 degrees there. Tetrahedral is when I've got 4 things bonded to it, and my bond angle is 109.5 degrees.
I don't understand, how is it 109?
How is it 109?
Like,
Some scientists got
what
a
makes it
little
what, how can
atom
you,
size
360 degrees, how do
Okay,
you
yeah,
divide
that
that
was my question too. Every time.
by 4 and get 109?
A really smart chemist got a little atom-sized protractor and put it down there.
Because you're thinking of just a circle being 360 degrees. We're not looking at just one circle here. I'm going always.
So how many degrees?
Okay. So between here and here is 109. I'll flip it here, here, and here. I'll flip it here, here, and here. I'll flip it here, here, and here.
So what do they all do?
Yeah, once I start thinking about it.
Okay. They don't get out of your head that they have to equal 360. The only way they would just be 360 is if they're flat, which these two are. These two are flat. Okay? Which is why this is 180, because it's 180 this way, and then if I went that way, it'd be 180, which equals what? 360. Trigonal planar is flat, which is why every way I go is 120, and if I do 120 times 3, I get 360, because the circle is 360 degrees. When I move into these, now I'm talking 3D. We're not laying flat.
Z.
Okay, exactly. You've added the Z. Now I've got X, Y, and Z. Okay, so now I'm not just on an X, Y plane. Now I'm 3D. So you can't put in your head this all has to equal 360. It doesn't.
But it doesn't. What if it doesn't equal anything like a certain number?
I don't think so. No, it doesn't. I know that for a fact.
So,
I agree. So it's just something you got to memorize. Okay.
Really?
And I'm not big on memorization in chemistry, but this is one of those things where you just got to memorize it. Okay. Bent is when I have something like water, where it would be linear because there's only 2 things bonded to it, but because of those lone pairs, it pushes them down, so it gives me a bond angle of 104.5 degrees. Okay. Trigonal bipyramidal, of course, is when I have something with 5 things bonded to it. So I have 3 things at 120 degrees, and I have 2 things at 90 degrees.
We have to like identify which ones.
No, you want to identify which one's which. Octahedral is when I have 6 things bonded to it, and everything is at 90 degrees.
Can you also go over when we need to put like a number on instead?
Okay, I can do that. So let's look at something like CO2. Okay, so how many valence electrons does carbon have? 4. Okay, how many does oxygen have? 6. Then I have to multiply that times 2 because I have 2 of them. So 4 plus 12 is 16, divided by 2 is 8. So I know I need 8 pairs of electrons. Okay, so let's put our carbon in the middle, and let's just pretend I single bond everything. Okay, so then I put my lone pairs around my oxygen, put my lone pairs around my oxygen, and if you count that up, you would go 1, 2, 3, 4, 5, 6, 7, 8, and a lot of people would leave it right there. What's the problem with that drawing? Carbon has to have 4, right? Everybody's got to have 4. Now, if I go 3rd period or greater, I can get more than 4, but everybody still has to have 4. Here's your exception. Unless you're boron, then you're okay with 3. Okay? So let's say I go in and I say, okay, well, I'll just put lone pairs on carbon so that it'll have all 4. Well, then what's my problem? Well, now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 pairs of electrons, and we just said I'm only supposed to have what? 8. So that lets me know I've got two too many. So now I know I'm going to have to form 2 double bonds. So if I take away those lone pairs on carbon, and I make this a double bond, that means I've got to take away these on oxygen, because oxygen's on the terminal end. It only wants 8. So now if I count up, I've got 1, 2, 3, 4, 5, 6, 7, 8 pairs of electrons.
Would it always be kind of like that where you take off like one from like the...
Yeah. You'll have to take them off to fix them. Does that help?
Yes, sir.
Okay. Let me know if it doesn't. I don't mind answering. Huh? Scroll back up. There? Is that what you're wanting? There you go. Alright.
So
Let's
if you're doing just like a regular molecule,
Uh-huh.
without 2 double bonds, you just take one away from like the one it's double bonding with, and then just take the double bond and come out.
No, I don't know what you're talking about.
Kind of like if you had to double bond in a molecule, you had to do it only on one. But like, would you take away one of its electrons and put the double bond like there?
Whatever 2 that you put the double bond between, you've got to take away a pair of electrons from both unless you're giving it a double bond to satisfy the octet rule. Anything that's on the outside of the atom, that's on the terminal end, can only have 8, period. And the only way it can have more than 8 on the inside is if it's in the 3rd period or greater. Okay? Other than that, just base it off of everybody has to have 8. I don't care how I get it on there, I've got to give them 8. And it's got to follow my rule on how many pairs that I'm supposed to have. Yes, sir. Just wait. Remember, what's the difference between a weak acid and a strong acid? There you go. Strong dissociates completely and a weak what? Does not dissociate completely. They're going to give you some drawings and ask you which one's the correct drawing. You need to remember that rule. Okay? You need to look at that graph in your notes where it had energy as increasing, and then it drew this, and it asked me where would be the best bond length for the hydrogen. And remember, it's wherever there's the least amount of what? Energy. Okay. So you should get that question. I'm going to be upset if you don't. Okay. Remember, for it to have a 0 dipole moment, that means everything has to be spaced out how? Equally. Okay. Remember, if I asked you something like CaO versus NaCl, okay? And I said, how come this one has a higher melting point compared to this one? Okay? It's because calcium's positive 2, oxygen's negative 2, sodium's positive 1, chlorine's negative 1. And remember our Coulomb's force law? Where these two are the what? What's Q1 and Q2? Charges. So the greater the charge, what's going to happen to my attractive force? It's going to go up as well. And the more strongly attracted we are to each other, what happens to my melting point? It gets higher.
I feel like we're gonna be good on this, but I don't want to jinx it.
Okay. If you know that geometry, you're going to be good. And there'll be a couple I'll give you because they pulled it from the next test and brought it back, assuming you remember from last year. I'm not going to assume you remember from last year, Olivia. And then it asks questions like, which of the following contains 1 sigma and 2 pi bonds? So that means I'm looking for a what? Triple bond, right? Everybody remember that? Okay. If it's got 1 sigma, 2 pi, that means I'm looking for a triple bond. So I'm looking for the molecule with a triple bond.
What about that formal charge thing?
Formal charge, we'll talk about that in just a second because you do need to know that. And then bond order. Formal charge you're not going to need to know until for your response. So let's get through multiple choice right quick because you'll need that tomorrow. So bond order, remember, like if I have Br to Br, that's how I would draw it. bond order is this? 1. Why is it 1? Because it's a single bond. What bond order is that? 2. Why is it 2? Double bond. What bond order is that? 3. Why is it 3? It's triple bond. Okay? Out of these 3, which one has the shortest bond length?
The 3.
This one, right? Because it's a triple bond. A triple bond is shorter than a double bond, which is shorter than a single bond. Okay? Why? Because remember we talked about electron density. The greater my electron density, what happens to my bond length?
It's short.
It gets shorter. Okay? Why? Because all those negative electrons are doing what to these positive nuclei? Making them move in closer, right?
So when you form a triple bond, it's kind of the same as like forming the double bonds.
Yep. And then hybridization is on there as well. It's on the test. So make sure you understand hybridization. And then what Hope was asking, I got 2 minutes. We're going to see if we can get this in. And she was asking about formal charge. Okay. They're going to give you 2 different molecules. I'm going to give you the example I gave you in your notes. Okay. Right. They're going to give you 2 different molecules, and they're going to say which way is the best way to draw this. And they're going to ask you to do it based off of formal charge. Okay? So how do I do formal charge? Well, let's do formal charge on the single bonded oxygen versus the double bonded oxygen first. Okay? How many valence electrons does oxygen normally have? Just a regular normal atom, not bonded. 6. And how do I know that? Because of what column it's in the periodic table. Okay? So that's what I do first. There's its group number, 6. Okay? Minus, then I look at oxygen and I say, how many belong to just the oxygen? So 1, 2, 3, 4, 5, 6. And then you know how this single line represents 2 of those electrons? We only count 1 for belonging to oxygen. So 7. Because they're sharing them. So 1, 2, 3, 4, 5, 6, 7. So I do 6 minus 7 is negative 1. So the formal charge on this oxygen is negative 1. So that's going to be the formal charge there and there. Okay?
That's close to 0.
So if I look at the double bonded one, I say oxygen normally has 6 valence electrons. That doesn't change. How many belong to just this oxygen? 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. So I can already tell you it's probably going to be the second molecule because we're looking for the formal charge closest to 0. And then you would do the same thing with the xenons, and that's how you get formal charge. Okay?
Basically, if it has a double or a single bond, then it's going to be.
Not always. No.
What do you mean for like the xenon? Like you would do like what?
You do
column
the
it's
same,
in,
yes.
And then you would just say it has like.
It has 1, 2, 3, 4, 5 that it has by itself on that one. Does that make sense? Okay.